All right, so the next homework assignment, the last one, I've given you the paper copy of that. It's also posted on iLearn. That on the schedule is set for being due on Sunday the 3rd, but I've pushed back the deadline to the 5th since there was nothing else being submitted that day. So you can take until Tuesday the 5th for that one, but then the main thing you should be thinking about over the break, I hope, at least part of your time, is the final project. And so the papers need to be submitted in two ways, both in paper in class, and then the digital copy should be uploaded to iLearn by Thursday the 7th. And I've mentioned this before, but the main idea with this final submission is that you take the updated draft that you produced for Part 1, the updated draft that you produced for Part 2, after taking into account my feedback, the feedback from the Writing Center, and hopefully just some additional research along the way. And that's what the final submission will be. Today we're going to talk more about hazardous waste management and specifically how to do calculations on a packed tower column. With hazardous waste management, the waste has to go somewhere. As long as we are using substances that are dangerous to the environment, we have to have what they call a cradle-to-grave tracking and disposal system. And what cradle-to-grave means is that the company that's producing the chemical has to keep very detailed records of how much is generated. The shippers who move the chemical from place to place have to have a log that shows how much they received, how much was delivered, and so on. The consumer of the chemical has to account for, on a mass balance basis, how much was used. And in the homework you have a problem where I ask you to do a mass balance, and what you should do is think about the black box concept, where there's things going in, things coming out, and they can go out of the so-called black box in multiple locations. It may be a sludge where some of it goes. It may be what they call drag. And drag is when, for example, if a part is submerged into a chemical, when you take it out of the chemical, it still has a little bit of the liquid on the outside of the part. So that's in the homework what it means by drag. And then there's also evaporation. And so in a mass balance, we're going to assume that there's no accumulation inside of a control volume. And so when accumulation is 0, in equals out. So the consumer of hazardous material has to do something like this just to show where it all went, to prove that they're not cheating. And by what I mean by cheating is it's very expensive to dispose of hazardous waste. And so there is an incentive to try and get rid of it maybe in unethical ways. If you were just flushing the hazardous waste down the toilet or pouring it into a river or burying it in the sand, all those things would be a lot less expensive than a secure landfill or incineration in a specialized facility. So the cradle-to-grave tracking of hazardous chemicals is a way of making sure that it doesn't get into the environment. So what we do in this management process is, as much as possible, we concentrate the waste so that there's less volume that has to be treated. And that principle of concentration is what they were doing when we visited the wastewater treatment plant. When they had the sludge in the drying beds, they could take the wet sludge to the disposal area. They could take wet sludge to a landfill. But when the sludge is 97 or 98% water, that's very non-economical. So by concentrating the waste, what they were doing is they're laying it out in a bed and just allowing the water to evaporate and leaving the solids behind. Disposal is, once you've concentrated it as much as possible, trying to find a secure ultimate location. And finally, remediation is just the cleanup process that sometimes has to occur when there's an accidental spill or when people are polluting illegally. We'll talk about each of these three things today. So first, let's talk about just one of the methods that are used for concentration. And I should mention that in the text, there's dozens of examples of each one of these. And so we're just going to scratch the surface. Unfortunately, we only have 2 lectures for hazardous waste, so we don't get into the same level of depth that we could. In an ion exchange, what it is a special resin, as it's called, and you could think of it maybe as beads. There's some sort of beads in there that have the ability to attract whatever it is we're trying to concentrate. This is used for water softening, but it can also be used for the removal of hazardous metals. Usually when we're doing water softening, we're just getting rid of hardness ions like magnesium, iron, manganese, and those aren't necessarily toxic to us, but there are things that we'd need to remove like chrome, zinc, copper. The concentrations could be high and dangerous. And so the removal of heavy metals can sometimes be accomplished by directing the water through the top of a column like this that's packed with the special media or packed with the resin. And over time, this resin can absorb a certain amount of the metal, but then it's going to lose its effectiveness. And so now what we have is we've got this, this column that's loaded with the pollutant. And so the pollutant has been concentrated, and it has to be regenerated. We have to somehow flush this column. We have to rinse off the beads that are in there and increase its ability to absorb the pollutant again. And so when you're doing what's called backwash, you're redirecting the regenerant through the beads, you have to recollect the extra water. So you're going to send the water the other direction, this regenerant that makes the resin work again, and now the waste is concentrated, so that originally when we were treating the water that went through here, the concentrations of the metal were probably low. But it accumulated inside of the tank, and then during the backwash process, we'll have less volume than originally went through there. So there's still some waste that has to be disposed of, but it's a way that we can concentrate a liquid waste. No, you wouldn't put it back through again. Let me draw on the board here. So what we would say is maybe for 24 hours, we have water going this way, and so the dirty water goes in, and the clean water comes out for 24 hours. But then this becomes full. Whatever it is we're trying to remove, let's say if it was chromium, this becomes full with the chromium, and so now we have to get it out, because once it's full, then it can't clean the water anymore. So we have to stop the dirty water from coming in during the regeneration process. And let's say it's going to take a smaller amount of time, maybe just only for 1 hour. What we would do is we would redirect this regenerant through here, and then out of the top we would take very dirty. So it had maybe low concentrations before, but now because we're going to flush this out in a shorter period of time, if we're flushing it in only 1 hour, then this is going to be very dirty. The point is that this is more concentrated, so we have less volume. So we had 24 hours worth of clean water and only 1 hour's worth of dirty water. And so the volume that the pollutant is in is lower. And let's say, what are we going to ultimately do with the contaminated water? If we're going to mix it into a concrete and then landfill the concrete, now we have to get rid of a smaller volume. So we're getting rid of the hazardous metal, but it's more concentrated, and so it's cheaper. You can't always use evaporation. Sometimes you can, but not always, especially if whatever you're trying to remove would cause air pollution that's dangerous. So some things you can evaporate into the air without worrying too much, but this is just one of the tools that we can use to try and reduce the overall volume of polluted water that has to be dealt with. Mm-hmm. It usually is something special, the regenerant. It's something that's causing a chemical reaction with the resin that's releasing whatever is stuck. So when the regenerant isn't there, the resin will attract the pollution, but then when you put in the regenerant, it releases the pollution. That's a good question. All right, so another way to concentrate waste and try and reduce the overall volume that has to be treated is with what's called electrodialysis. Now, who's heard of dialysis before? Not the electro part, but just dialysis. What's dialysis related to? Right. What organ is it? It's the kidney, yeah. And so what the kidney does is it removes pollutants from the blood, and when some people have kidney disease, then they may lose the effectiveness of both of their kidneys, and so dialysis will filter the blood and remove the pollutants. So this is a similar process. What it does is it uses a charged electrode to try and draw anions and cations away from solution. So it's a way of concentrating and isolating things like metals. Now this only works for ionic pollutants. It wouldn't work for an organic chemical. But as long as it's something that a charged pollutant, then the negative charge here, the cathode, is going to attract any positively charged metals. And so there's a membrane here. A membrane is just sort of like a permeable barrier like plastic that has very small holes in it. And the thing that's driving the separation of the anions and the cations is the charge. And so once we have all of the metals attracted to the cathode, then you could move the cathode, release the charge, and then the anions would be concentrated. Yeah, into water. And so imagine if there was a reactor, like here is, we're looking from above, and the water is coming in, and then it goes out. And so we have here a very long, we'll put the anode on the right side and the cathode on the left. And so the water is flowing through, and in the middle is a membrane, so like a plastic barrier. And normally those anions would stay wherever they're at, but the charge drives them through the membrane, and then they can become accumulated.
Is there a need for circulation?
Mixing?
Well, I mean, like, you just pump it and then you like put it again.
Oh, well, it depends on the input concentration and the output concentration and how efficient it is at removal. You may need to recirculate. It may be only able to remove a certain fraction each time through. All right, so those were just two brief looks at how we can concentrate pollutants. We can also incinerate them, and incineration is something that has to be pretty tightly regulated to make sure that there isn't just pollution that's getting into the air. You don't want to move it around. You'd like to concentrate it. And so let's take a look at this process and see how they're combining both a liquid waste and solid waste into the same incinerator and what the output products are. This is a good example. It's from the text because it shows the mass balance approach and how in a real world you have to keep track of where the contaminants are. And so the solid wastes may be just ordinary municipal waste, or it could be hazardous, but combining the liquid and the solid together, one of the things they're doing in the afterburner chamber is they're burning it at very, very high temperatures. It's not just whatever temperature can be supported by the solid waste, but sometimes they'll use high purity oxygen, mix it with gas, like natural gas, and if the temperatures are high enough, then they can help ensure that there is complete combustion. Because incomplete combustion is what really causes smoke, and there are some contaminants that have a very high burning point, and so we're talking like more than 1,000 degrees would be a typical temperature within the afterburner. Another thing I want to point out is look at what they're doing with the gases. The fumes or the output gases from this burning chamber, they have to put through a wet scrubber. Inside the wet scrubber there's like a spray, and so that any particles that would be coming from the exhaust fumes, or if it's a caustic gas like an acidic gas, those materials are absorbed by the water, and then the water has to go to a separate water treatment assembly. Another thing they do to try and remove particles is an electrostatic precipitator. And that's a little bit similar to what's happening with electrodialysis, except for that in this electrostatic precipitator, we're trying to remove charged particles from air, not from a liquid. And so ultimately what goes out of the exhaust stack has been, number one, burned at a very high temperature. Number two, has gone through a wet scrubber and then through a dry treatment process as well. And so what you have to dispose of is the residual solids, the ash. And that's going to be a much, much lower volume than the waste that originally went in. But it comes at a high price because these generally are using a lot of energy to get the temperatures high enough to break down all of the contaminants. Any questions about this diagram? Yeah. I think in the case of hazardous waste like this, they're pretty cautious about incorporating it into anything useful, so they'll just dispose of it. There may be exceptions, but the liability of using hazardous waste ash is probably high enough that it's just safer to landfill it. Let's take a look at this figure. It's included in your homework. The purpose of a cap, what we're looking at here, is to make sure that no water gets in to the hazardous waste landfill. Now, a hazardous waste landfill, as you might expect, has much higher standards than just ordinary municipal waste because what you're storing is so much more dangerous than just rubbish. So what we look at here is, number one, there's a drainage layer on top of the geomembrane. The geomembrane is the thick layer of plastic. And by putting a specific drainage layer on top of it, what they're making sure is that there's no pooling of water on top of the geomembrane. Because if puddles form, then those puddles can be very dangerous. It creates a pressure that has to be relieved, and over time the geomembrane could fail. So a drainage layer is important, and it looks from the diagram like this is flat, but they wouldn't make the cap flat. They'd have a slope so that any water that falls onto the top of it can drain away very easily. One thing I want to point out, this is a picture of a landfill in Atlanta, Georgia. You can get an idea of how big it is by the size of the freeway that's going by. This is a very, very large road, and so this is an enormous landfill, and they're trying to do something useful with the land. Once the landfill has been capped, you can't build on top of it, and so they've got some vegetation on it to try and help remove the water, evaporation, and protect the cap. But another idea they had was to put some solar panels on the top. And so we can't put anything too heavy because it could threaten the integrity of the cap, but solar panels are light enough that that's one of the few useful things we can do with land that's been used for landfilling. The other thing that's unique about a secure landfill is that there is two different drainage systems underneath. And so you may occasionally have things coming through this first layer of drainage pipes, but the second layer of drainage pipes is actually more of an emergency alert system than to remove any liquid, because if you notice anything coming from this bottom layer of drainage pipes, that means that the geomembrane underneath the first layer has been ruptured. And so it would be the sort of thing where they wouldn't say, well, we can just use this secondary drainage pipe as a backup system and continue normal operations. They would actually have to start excavating the landfill and searching for the breach in the liner if they start to detect anything in the secondary drainage layer. The other thing that's unique about a secure landfill is that the layer of compacted clay would generally be quite a bit thicker than is used for a municipal landfill.
Sir,
Mm-hmm.
what's the waste on top? Is this
No, this is, so here's the cap, and then this is the liner underneath. And so here's the waste, and not shown here, here's the waste as well. So above this is going to be more waste, and then the cap above it. All right, here's what we're going to do some calculations on today. It is a air stripping. It's a remediation technology. When the pollutant gets out into the environment, we have to do things to try and fix the situation. In air stripping, we're spraying a contaminated water at the top of porous media. The water trickles down while air is being blown upwards. And this should remind you quite a bit of the trickling filters we talked about during secondary treatment, because there are some real similarities here. What we're trying to do is we're trying to use air to strip out the organic chemical, the VOC, where this abbreviation stands for volatile organic compound. Volatile is something that will evaporate. So we're giving this a special place that the evaporation can occur to try and get it out of the water that's there in the first place. And so we're spraying water at the top, blowing air from underneath, and the air that comes out is going to be contaminated. And so sometimes we have to run this contaminated air through a carbon filter. Other times it's just you let it into the environment if the pollutant isn't too bad for the air. But the water is clean that's coming out. So here's the equation that describes the required height of an air stripping column. And you can see that how tall the column has to be is in part related to the cross-sectional area of the column. So if you have a very wide column, it doesn't have to be as tall. But there are a lot of other factors in here as well. C1 and C2 are referring to the inflow concentration and the outflow concentration. And so you have to look at what's the legal limit for this pollutant in the effluent. So you want to find out what should the C2 be, and you know the C1 because that's measured in the lab, the concentration that's coming in. The temperature of the air has an effect because the warmer the air is, the easier it is for gases to dissolve from solution into the air. Easier for them to go into the gas phase. So here you've got the definitions. In the in-class exercise, I've given you a problem statement that's similar in nature to the homework. So let's take a look at how tall the column has to be when we have the situation that's described here in order to get the concentration down below 1 microgram per liter. You have to have the G, which is the airflow rate, and L, which is the liquid flow rate. They both have to be in terms of cubic meters per minute. And then the temperature should be in terms of Kelvin. So the cross-sectional area you can find from the diameter that's given. And from there, you just plug in the rest of the knowns to the formula, and we find out that the column should be 1.6 meters tall. Okay. And obviously there's going to be physical restrictions on how tall a column could be. If you're doing these calculations and it tells you that the column needs to be 90 meters tall, well, that's not reasonable. And so what they do is they'd have them operating in series, where you'd have the water from one of the columns then going to the top of the next one, going to the top of the next one, and so gradually it would be reducing the concentration of the pollutant over each successive column. So this is just one of the methods that's used for remediation. It's really interesting to see all the genius ideas people have come up with to figure out how to deal with contaminated soil and contaminated water. It's everything from using gigantic electrodes and literally turning the contaminated soil into a big block of glass And that's a process called in situ vitrification. Very, very high voltage electrodes can immobilize a pollutant and make it so that it's not going to leach into the soil anywhere. Yeah. Mm-hmm. Excuse me? Oh, the sand. Won't the sand blow away? Good question. I've wondered the same thing about roads. Like I've noticed as I'm driving out to Kalba, like there's a road that's going up and it seems like the sand would just blow away. I don't know how they deal with that. Some of them seem like there's not too many trees around. I don't know. That's a good question. All right, let's take one last look at these announcements. The homework is due on Tuesday and the project on Thursday. So have a good break. Please put your in-class exercise on the table on your way out. Yeah.